Okay, today let us learn about CNN, the convolutional neural network. These things have come into picture in year around 2012. We know that the difference between machine learning and deep learning, one of the difference, major difference, that here this is manual feature extraction, whereas in deep learning we have automated feature extraction. We need not tell what features are important and what features are not relevant. This. Now, CNN belongs to the paradigm of deep learning. Let me give you some history about this. There is a database called ImageNet dataset, which has a large data set of digits. And these people, they every year they conducted a competition, large scale visual recognition challenge competition, and they used to invite uh, scientists across the world to participate in this competition. There are five categories: image classification, given an image, uh, whether it is man or woman or cat or dog, image classification, image recognition, segmentation, this thing. The simplest application that we do daily is whenever we use our phone with face unlock, what your phone is doing is it is recognizing your face, your image. So with facial attendance recognition, attendance or phone unlock, there everywhere we are using CNN. So where I am, we are talking about large scale visual recognition challenge. Let me show you the results of that. So this was image classification performance in that ILS VRC. So this ImageNet data set, it has over 15 million labeled high resolution images belonging to 22,000 categories. And with 2010, they conducted annual challenge where they use a data set where 1,000 images are there and 1,000 categories. And they used to have 1.2 million training images and 50,000 validation and 150,000 test images. So this ImageNet large scale visual recognition challenge was conducted every year. And the results are very interesting to see that in 2010, the error in classification, that means accuracy is opposite of that 1 minus error. So here the uh, error was 28%. That means the accuracy was 72%. Then in 2011, the accuracy was 74%. Only 2% has been increased. But if you see in 2012, the accuracy has gone up to 84 from 74. That means there is a huge shot up in the classification accuracy. This has happened because in 2012, there came a CNN, convolutional neural network, and they it is known as AlexNet. So they used this architecture of convolutional neural network. They also called it supervision. So today we are going to see what are the building blocks of this convolutional neural network. Uh, so in any CNN, there are let me check the color. Okay. Firstly, there will be a convolution block. Convolution block. Number two, there will be a pooling block. And in between them or after the pooling, we also use activation. What is the purpose of activation? To introduce the nonlinearity. What activation function you know? We know that there is a ReLU, there is a tan H, and there are some variations of ReLU known as Wiki ReLU, then truncated linear unit TLU. This is activation. And fourthly, there will be a fully connected layer. All the features extracting layers will be connected. Then finally, the classification or softmax layer. So these are the building blocks of any convolutional neural network. So let us unpack one by one what to understand what actually happening in convolution. Let us try to understand the concept behind the convolution. Convolution means moving one function over the other. Moving one function over the other. Let me show you a demo where we can understand the thing here. Here I have two functions. One is a squared function, that is function, this is squared function, and here I have another function, triangle function. Now if I move one function over the other, let us say I will keep this function here as a constant. I will bring it here and I will move that function over the here. Then I will get another generated function. See this animation? This blue function is being convolved. This red function over that, and because of that movement, we are getting another function by tracking what is the path of that convolution. So this is convolution, one over the other. To understand it in our purpose, uh, let us see. Let us assume some time series data. Suppose you are tracking distance or how an aeroplane is traveling. So I am taking the x coordinates of that aeroplane. At present, the coordinate is 10. Earlier it was 8, then it was 6, then it was 4, then it was 2. Now, when I'm calculating the present position based on the previous position, what I do is because these are not very accurate measurement, what we do is we take an average of the previous three values, and providing weightage to each value. Because it was the recent value, I will give zero point 0.5. This is the earlier value, so I will give the weightage 0.3, and this is 0.2. So the new value is 0.5 into 10, 5, 0.8 into 2.4, 7.4, 7.4 plus 1.2, 8.6. This is my new value. What I will do next? Next, this the present position will be 12. Then I will move this filter here. So 12 into 0.5, 6, 10 into 0.33, 6 plus 3, 9, 9 plus 8 into point, that means 9 plus 1.6, 10.6. So this is how we'll be convolving. Let me show you that which has shown last class also. So this is one function, this is the filter. We are moving that filter. This is known as convolution. Now coming to the images, what we do is we take filters. Now depending on the requirement, we will take different filters. For example, I am taking, we call this second function as kernel or filter. We have image input, and we will be moving this filter over that image. Something like here. So this is a filter. This filter will be moved like this. This filter will be moved like this. Is known as convolution. So what is the advantage of this? What actually is happening in the convolution? The convolution extracts different features based on the kernel. For example, I want to find in my image the edges. So what I can do is when I place my filter, I will keep all the other values untouched, and I will darken the central pixel. I will darken the central pixel, and I will keep all these things. So what, suppose my image, which is there, suppose it is having these values. Let us say this is, yeah. When we keep this filter 1, 1, 1, minus white, 1, 1, 1, 1 here on this, so this convolution will be calculated something like this. So 1 into 0, 0, 1 into 0 plus 1 into 0, 0 plus 1 into 0. So let me write it here, 1 into 0 plus 1 into 0, 1 into 0 plus 1 into 0 plus 1 into 10 plus 1 in minus 8 into 20 minus 160, then 10, 1 into 10, 10, 1 into 5, 1 into 10, 1 into 10. So all these things will be added and it will be placed here. So this is input, this is convolution, this is called feature map. By varying these filters, we can extract different features. Now you can see that this is convolution. So this is our input A, B, C, D, E, F, G, H, I, J, K, L. Now this is my 2 by 2 kernel. I will place it here in this position. So how it will be calculated? A into W plus B into X plus E into Y plus F into Z. This is one. Then here C into W, D into X, Z into Y, H into Z, H into. Then I will place my, if I place pixel here, filter here, B into W, C into X, F into Y, Z into Z. This is another pixel. This is known as convolution. So by different pixels, suppose if I keep all my ones, what will happen? It will blur the image. Why it will blur the image? Because I'm convolving, I'm multiplying with this kernel and I'm adding all these pixels and I'm placing it in a lower dimension matrix. So because of that, it will be convolved. Now look at this one. This will sharpen the image because uh, it is highlighting the middle pixel with 5, multiplying it with 5, and remaining things it is making 0 or minus 1. So because of that, whenever this filter is placed here, so middle pixels will be brightened more and your image will be sharpened. If you take another filter, which is just now I told you, edge detection filter, so minus 8. So what it will do, it will darken the middle pixel and these will, all the edges will be highlighted. So this is convolution. Convolution. So we'll see a demo provided here. Now here I am selecting from Amnist database. I am selecting any number. Let me take maybe 8. I think that is, and I will take top edge filter. That means what it will doing. It is darkening the top edge and it is keeping this middle one same and it is making 0 the bottom one. So these edges will be brightened. This one here and this one. So if I might place my pixel here, it will multiply 0 into minus 1 plus 0 into minus 1 plus 0 into minus 1, 0 into 1 plus 0 into 1 plus 0 into 1, 0, 0. So it will place that here. So here I'll place my, you can see there is nothing because all are zeros. Your output is also 0. Bear with me. Let me bring that here. So when I bring the pixel here, you can see the middle values are multiplied with 1 and the top value will be multiplied with minus 1 and the BD's bottom will be 0. So what is happening? Those are being highlighted. That means it is extracting all the top edges, all the horizontal edges. Suppose I want to extract all the vertical edges. What I will do, I will take left edge filter. I want to extract all the vertical. So you can see here, it will extract all the vertical. So by using a series of many filters like this, I can extract different features of a given image. You can also see another, yeah, that's enough demos. So this is convolution and feature. Now let us get into some mathematics of this. For example, I have W by W image size. For simplicity, let us assume that our image is squared image W by W width. So I can take W and kernel is K by K size. So if input is of size W and kernel is of size K, what will be the feature map size? What will be the size of the output? It is very sure that output size will be lesser than the W because we are we are summing up of filter values and we are placing in a single value. So the feature map size will be, if it is W and it is K, I can place my K in W minus K plus 1 times. So my feature map size will be W minus K plus 1. W minus K. This is the very, very important aspect to understand. That means if I have size of 5 by 5 is the size of my image map image and I have 2 by 2 kernel, then 5 minus 2, 3, 3 plus 1, 4. My feature map will be 4 by 4. If I have 5 image size and I have 3 by 3 kernel, 5 minus 3, 2 plus 1, this will be 3 by 3 image. Now, when we use 3 by 3 or kernel, we focus on central pixel. But the problem is when I keep it here, my convolution is starting with 20. When I move that filter here, it will be 10. But these pixels are not being convolved. This minus 8 is not being placed in 0 on this first. So what we do to convolve these also, we use a concept known as padding. What we do is to keep it here, we will add a dummy row and I will place my zeros here. And obviously this one also on the top, on the bottom, and on the left and on the right. So when I keep my filter here, this minus 8 is placed on 0. So this adding zeros on the top, bottom, and the left and right is known as padding. Padding. There are three types of padding. One is called valid padding, where we don't use padding. And if because of the padding, the output feature map size will increase and you will not lose any information. So if your output feature map, that means output of convolution, the size of that, if it is same as the input size, then we call that type of padding as same padding. Same padding. If all the pixels undergo the same number of convolutions, for example, here 0 is undergoing only one convolution, whereas 20 is undergoing different number of convolutions because it is in the bottom. So it will be here, it will be here. When we place your kernel here, 20 will undergo convolution. If you keep your kernel here, it will undergo. So if all the pixels they undergo the same convolution, same number of convolutions, then it is known as full padding. So how many types of padding? Valid padding, no padding. Valid, no zeros. Same output feature map size is same as input image. Then full padding, generally we don't use full padding, we use only valid and same padding. Full padding, all the pixels will undergo the same number of convolutions. Now let us see the padding. Then one more aspect. Suppose once I place my, let us look at another concept called stride. Suppose I place my filter here, 3 by 3 filter. I will place my filter. The next step is I will place my filter here. This is known as stride 1. Then I will place it here. That is known as stride 1. Instead of that, if I skip after placing my kernel here, if I skip the first second row and I will keep my kernel here, then it is known as stride 2. Because of the striding, your output will be having very less size. Striding. Stride 1, no gaps. Stride 2, you will leave out one thing. So coming to the mathematics of that, output feature map size, we have already told that W minus K plus 1. So if you add padding, padding will be in two sides. So if you add two, if P is the number of pixels you are adding, so your output feature map size will be W plus 2P. This is your new image size minus K plus 1. If you are using stride S, then the output size will be W plus 2P minus K by the stride plus 1. So your stride will reduce the feature map size drastically. You can see the uh, pooling demo, sorry, not pooling, stride. So this is about convolution, padding, stride. In the next session, we'll talk about pooling, which is very, very important aspect. In before I close, let me tell you what are the advantages of the convolution. In previous dense network or uh, in deep feed forward network, if you have 16 inputs, all those 16 inputs are connected to each of the second layer. That means you have 16 weights. But whereas in convolution, these 16 are connected to only 4 weights. So H1 is a resultant of this 16 multiplied with these 4 only. 4 here, 4 there, 4 there. So this is known as sparse connectivity, where we have many missing values. That is the first advantage of CNN, sparse connectivity. Secondly, parameter or weight sharing. So when we go to the dense network, this weight is different, this weight is different, this weight is different. All the weights are different. But whereas in CNN, these weights calculated to H1, the same weights will be used to calculate H. That means on this layer, only I have to learn only 4 weights. This is known as parameter or weight sharing.